look at setting up a linear programming problem. So the scenario here is we're going to have a business where we're going to teach algebra and arithmetic skills to students. We're doing a combination of online instruction and in-person tutoring. So we've determined our business model will have a profit for each algebra student set at $2 and $1.25 for each arithmetic student. We want to determine the optimal mix of students to have to maximize a profit but stay within our business constraints. So profit isolines show different combinations of students that yield the same total profit for our company. For example, a profit of $200 could be had by having 100 algebra students, since we get $2 profit per algebra student, but no arithmetic students. Or we could have 160 arithmetic students at $1.25 each to get $200 and no algebra students, and that would still give us the same profit of $200. And then there's multiple scenarios in between there of combinations of algebra and arithmetic students. What we're doing, again, is trying to find the optimal product mix. So what's the best mix of algebra and arithmetic students for our company? So that example is just for a profit of $200. We could say come up with a profit of $400 by having 320 arithmetic students and no algebra students, or no arithmetic students and 200 algebra students would give us the same profit of $200. So just to visualize this, graph here. On the x-axis, I have the number of algebra students, and on the y-axis, the number of arithmetic students. My blue line here is a profit iso line for $200 profit. Every point on this line represents a combination of algebra and arithmetic students that gives us a profit of $200. So as we said, 100 algebra students and 0 arithmetic students, or 0 algebra students and 160 arithmetic students, and then combinations in between, say 50 algebra students and 80 arithmetic students, also gives us a profit of $200. The red line represents the $400 profit isoline. So these are all possible points, combinations of algebra and arithmetic students that will give our business a profit of $400. So the more students we have, the more profit we make, and we make more profit on the algebra students. Isn't the answer just to sign up as many algebra students as possible if we're trying to maximize a profit? Well, no, because there's more to the problem than I've told you so far. The other part of the problem are constraints. So these are the constraints on our business. What are our limitations to what we can offer? So students use resources. We've got to support our students, and we're going to be using a combination of computer and in-person tutoring to provide instruction. So we've got it set up that our company has resources to handle a total of 300 hours of computer instruction. So we've got a computer server available. Students will log in, and it can handle up to 600 hours of computer instruction a week. And then we've hired enough tutors so that we can have 200 hours of in-person tutoring each week. And the way our business model is set up is the algebra students are allotted 2 hours of computer instruction, 1 hour of tutoring each week, and arithmetic students have 1 hour of the computer instruction time and an hour and a half of in-person tutoring. So we've got limits on the total number of students we can support because we only have 300 hours of computer instruction time and 200 hours of tutoring time. And also it's going to affect the mix of students we can support. So look at a few scenarios here. And by the way, if this seems tedious, this is not how we're going to solve the problem. This is just to get a feel for how the problem works, what's possible, what's not. So if we took all our computer resources, 300 hours, each algebra student uses 2 hours of computer time. So we could support up to 150 algebra students with that 300 hours of computer time. And then no arithmetic students because there's no computer time left for them. So in this scenario, those students would also use 150 hours of tutoring time. Then there'd be an extra 50 hours of tutoring that went to waste because we had enough tutors hired for 200 hours of tutoring. So if we had 150 algebra students and no arithmetic students, we would end up using all 300 hours of our computer time and 150 hours of our tutoring time. And that would give us a profit of $300 because each algebra student gives us a profit of $2 and we've got 150 of them. So there's a pretty good profit there. If we wanted a mix of students, say we wanted to have a mix of 100 algebra students and 100 arithmetic students, we have the computer time, but we don't have enough tutoring time for this to work. So this ends up being not a feasible solution. So just to walk through that, 100 algebra students and 100 arithmetic students. On the computers, each algebra student uses up to 2 hours of the computer time, so there's 200 hours. Each arithmetic student uses 1 hour of computer time, so there's another 100 hours, so a total of 300 hours of computer time are being used, which is how much computer time we have. For the tutoring time, each algebra student gets 1 hour of tutoring time, so 100 algebra students at 1 hour, there's 100 hours. And each arithmetic student gets an hour and a half of tutoring time, so there's 150 hours if we have 100 arithmetic students. That gives us a total of 250 tutoring hours, and we only hired enough tutors for 200 hours. So this isn't feasible. So looking at another one that mixes things up, say we had 50 algebra and 100 arithmetic students. So 50 algebra students on our computer time, 2 hours each would be 100 hours. 100 arithmetic students, 1 hour each would be another 100 hours. So that'd be 200 hours of computer time. So it'd be underutilizing our computer time with that product mix, 50 algebra and 100 arithmetic. On the tutoring time would be okay. 50 algebra students at 1 hour each would be 50 hours. 100 arithmetic students at an hour and a half each would be another 150 hours, a total of 200 hours of tutoring. So that would use up all our tutoring time. And that product mix would give us a profit of only $225 though. $2 for each algebra student, $2 times 50, $1.25 times each of the 100 arithmetic students, a total of $225. As you can see, this quickly gets very tedious. So there is a better way. Focusing on the constraints, again, we have at most 300 hours of computer instruction and 200 hours of tutoring available. Using our variables, x is the number of algebra students and y is the number of arithmetic students. It's going to organize the information we've got in a table here. So for computer instruction, each algebra student uses 2 hours of computer instruction. Each arithmetic student uses 1 hour of computer instruction. And we've got a total of 300 hours of computer instruction available. And for the tutoring, each algebra student's allotted 1 hour of tutoring. Each arithmetic student's 1.5 hours of tutoring, and we've got a total of 200 hours of that particular resource. As you're setting these up, you're going to find the constraints are probably the trickiest thing to get organized, so I really recommend trying to organize that information in a table. Then writing your equations. Okay, grab a pen here. So the number of algebra students is x. Number of arithmetic students is y. We have at most this much constraint, and so we get our first equation. I've got those in the wrong order, I'm sorry. There we go. 2x plus 1y less than or equal to 300. Our tutoring, 1 hour for each algebra student, plus 1.5 hours for each arithmetic students, within the constraint, 200 hours available. Okay, there are 2 additional constraints that aren't obvious at first glance with our problem. What's the least number of students we can have in either category? 0. We can't have a negative number of students, so we do have 2 additional constraints that x needs to be greater than or equal to 0 and y is going to be greater than or equal to 0. And these 2 constraints will show up in virtually all the problems we look at. Okay, we can then graph the feasible region and determine the corner points. So blue line is our computer resources. This is the 2x plus 1y less than or equal to 300. And then the tutoring, that was 1x plus 1.5y less than or equal to 200. Because these are less than or equal, our feasible region then is going to be this area in here. So this area in here represents the product mix that satisfies both of our constraints. We're going to stay in quadrant 1 because of the x greater than or equal to 0, the y greater than or equal to 0. We're going to stay below the red line because that's where we're less than or equal to 200 hours, and we're staying below the blue line because that's where y is less than or equal to 200. It'd be a little easier to see here. And so within this shaded area are all possible combinations of students that satisfy the constraints and have a feasible solution. So now we can find the corner points. I've actually got them listed here. This corner point's probably pretty obvious. That's a 0, 0. 150, 0 is this corner point right here. And 0, 133 is this corner point here. This one takes a little bit of algebra to find, 125 and 50. But we can use that taking our two equations, solving them as a system of equations. Okay, just added that in there. So if I take my two equations, 2x plus 1y equals 300, that would be my blue line here. My second equation, 1x plus 1.5y equals 200, that's my red line here. And finding the point of intersection, I multiply the second equation by negative 2. That gives me negative 2x, negative 3y equals negative 200. Solving eliminates the x. That way I've got y equals 50, and then once I've got y equals 50, I can go back to either the two original equations, plug in 50 for y, and solve for x, and I get 2x equals, let's see, subtract the 50, it would be 250, divide, I get x equals 125, which looks reasonable looking at the graph. X is 125 and y is 50. Why do we care about the corner points? Good question. If a solution to the system exists, if there is a point that optimizes the equation, maximizes a profit, it's going to occur at a corner point. Then we can, knowing that, we can take each corner point, systematically go through with our profit equation and find where do we maximize our profit. So at 0, 0, obviously we're not going to maximize our profit. If we have no students, we have no profit. At 150 algebra students and 0 arithmetic students, we get a profit of $300, which is pretty good. At 0x, 0 algebra students, 133 arithmetic students, our profit's only $166. And then at the 125 and the 50, we actually exceed our $300 profit and get a profit of $312.50. So that's our best mix of students. So what we're looking for with these problems, again, is what's the optimal product mix. Okay, then just to go back to a picture again, most of us like pictures. The two black lines here outline our feasible solution, and I've rather badly shaded it in here in pink. And then what I've overlaid here are some profit isolines to kind of visualize what's happening and why the corner points are so important to us. So this line, which kind of disappears here, is our $200 profit line. So let me just continue that on there. Every point on this line gives us a profit of $200. So any combination of students on this line would give us a profit of $200, and we can do better for our business. This profit isoline here is $400, and we can see we basically would need to expand our business, expand our constraints if we're going to get a profit of $400. It's just not feasible because none of our feasible points, we can't, because of the constraints, we can't reach this profit isoline. That's probably the best way to say it. And then I've thrown in a third one, a $300 profit isoline. That's this middle one here. And again, let me extend it out here a little bit. At this corner point, we did reach a profit of $300, but we could actually do a little better. At this corner point out here, we're a little further out beyond the $300 profit isoline, and that's where we reached the profit of $312.50. So that was our best solution. Okay, so we're not going to solve all these by hand. We are going to solve them in Excel much more efficiently. But what is key to these are getting all the equations, the variables, the constraints laid out. So that's the first thing you want to be thinking about before you go into Excel to solve these. Think about what it is you're trying to optimize. Are you trying to maximize profit? Are you trying to minimize costs? And what variables are involved? So when you've got the variables, you can write your equation that you're trying to optimize using those variables. And then what's going to be critical to moving on is when you list the constraints that you're using the same variables for your constraints. And each constraint is going to be a less than or equal to something or greater than or equal to something. And you want to watch that to be careful that you've got things set up correctly.